Thank you, Mike, for that very kind introduction and for setting up all the audiovisual stuff for me today. I'm very pleased to be here. It's very nice to be able to give this talk to my local audience, and so it's a nice thing to be here this evening. So our universe is a very dynamic place. It's a place where change can happen on timescales ranging from a few seconds to billions of years. Inside galaxies, stars are formed via the gravitational collapse of dense clouds of gas. And these same stars later die, sometimes in spectacular explosions and other times just quietly fading away. And this process of star birth and star death drives a slow evolution of the galaxies in which the stars live. Sometimes in our universe, two galaxies will collide, and these collisions between galaxies drive a much more rapid evolution, producing an intense burst of star formation and resulting in a new galaxy whose properties may bear very little resemblance to the two parent galaxies. In all these processes, the slow and rapid evolution, the process of star formation, which is critical, takes place inside very dense, cold clouds of gas and dust, which are impossible to study in wavelengths of visible light. So in order to understand the process of star formation and the galactic evolution which is driven by star formation, we need to move beyond the visible universe. So in my talk today, I'm going to start by giving you a brief overview of why you should be interested in understanding the invisible universe. I'm going to talk a little bit about the physical processes which produce emission at predominantly the far infrared and radio wavelengths at which I work. And then I'm going to give you a little overview of the types of scientific questions that we can address when we look at radio and far infrared wavelengths. I'm then going to discuss two related science questions. I'm going to start by discussing some studies of how stars form in our own backyard in clouds of gas that are very close to the sun. And then I'm going to discuss star formation in other galaxies. By looking at other galaxies, we can both put our own Milky Way in context, and it also lets us study environments that are very different from the ones that we can find in the Milky Way. And then I'm going to finish my talk by talking about the Atacama Large Millimeter Array, ALMA, which is currently under construction in the high desert in northern Chile and will have a huge impact on all the types of science that I'm going to talk about today. So why should we care about the invisible universe? Well, objects in the universe produce radiation across the electromagnetic spectrum, which is shown here. And our eyes are sensitive to a very small portion of that electromagnetic spectrum. The little rainbow in the middle shows you the wavelengths of visible light to which our eye is sensitive. Objects that are very hot will produce most of their radiation at shorter wavelengths than the visible, at ultraviolet wavelengths, at X-ray wavelengths, and if they're very hot and very energetic, maybe even up to gamma rays. In comparison, objects that are cool or even very cold will produce all of their emission at longer wavelengths, out into the infrared, the microwave, and the radio. So if we were to limit our study of the universe to the wavelengths of visible light to which our eyes are sensitive, we would miss large parts of the universe, both these very hot and very cold objects. Now in my talk today, I'm going to concentrate on the cool objects because those are the regions which are interesting for star formation. Now, in our universe as a whole, emission from cool objects is energetically actually very important. The dominant source of energy in our universe is the microwave background radiation, which is the cooling heat energy left over from the Big Bang 13.7 billion years ago. The microwave background radiation radiates at an effective temperature of just about 3 degrees above absolute zero. And it is the peak here at the long wavelengths. But the next most prominent peak in this plot of the energy distribution of the universe is in fact in the millimeter and far infrared portion of the spectrum. This is emission from cool objects, and these long wavelength photons dominate the spectrum of many interesting objects that we'd like to study, such as young stars, planets, and young distant galaxies. So there are two processes that can produce electromagnetic radiation at far infrared and millimeter wavelengths. The first process is thermal emission from dust grains. Inside clouds of gas, there are very fine particles of dust, about 1 micron in size, made up of silicates and carbonaceous material. These dust grains radiate heat energy in a very similar process to the way our sun radiates heat energy, producing all the visible light that we see, and the same way that our own bodies radiate heat energy that lets us be visible with infrared night vision goggles. Now, these dust grains, though, are much colder than the sun and even much colder than we are. They are typically 10 to 50 degrees Kelvin, 10 to 50 degrees above absolute zero, or about minus 260 to minus 220 degrees Celsius. Because the objects are so cold, the heat energy that they produce is shifted to the long wavelength portion of the spectrum, into the infrared and into the radio. This process of producing heat emission, whether it's the sun or us or these dust grains, has the characteristic of producing a very broad band of emission covering a range of wavelengths. And for these dust grains, the range of emission goes from about a wavelength of 10 microns out to a wavelength of about 3 millimeters. This slide shows you an example of what this heat emission looks like in different objects. And this is what physicists refer to as blackbody radiation. The top curve on this plot shows you the heat emission spectrum from our sun at a surface temperature of about 6,000 Kelvin. And you can see that the peak of the emission occurs at about 1 micron or a little shorter, right near the visible part of the spectrum. If you move to an object that's about 1,000 degrees, so this would be a low mass cool star, you have the same shape curve except it shifts to somewhat longer wavelengths. So now the peak of the emission is perhaps around 5 microns. And as you move to cooler and cooler objects, the emission spectrum shifts to longer and longer wavelengths. And the dust grains that we're interested in produce the peak of their emission around 100 to a few hundred microns. And importantly, produce no emission to speak of at visible wavelengths. So we can't see these things in the visible, but we can see them in the radio. The second emission process that's important in looking at cool regions of star formation is emission lines from simple molecules. Molecules can produce electromagnetic radiation in very discrete specific energy ranges or wavelengths. And they produce this emission by undergoing either a rotational or a vibrational or an electronic transition. The easiest analog to this at visible wavelengths would be to think about a neon sign. Neon signs basically shine because they contain atoms of neon, which are producing emission at a particular wavelength and that comes out in the visible and therefore is a certain particular color. This is a similar type of process, but again happening in the radio. Now, when we look at a region in which stars are forming, most of the gas that's there is in the form of molecular hydrogen gas. And this is because hydrogen is by far the most abundant element in the universe. However, hydrogen gas is a very inconvenient molecule from the purposes of trying to study it with radio telescopes, because it only produces emission lines when it's heated up to roughly 0 degrees Celsius. So hydrogen gas at the temperature that it is outside today would shine. But hydrogen gas in galaxies where it's typically 10 or 50 degrees above absolute zero, again minus 240 Celsius, doesn't shine at all. It's totally invisible. So what we do to study the regions that contain hydrogen gas is we look at trace molecules which are mixed in with the hydrogen and which do emit at radio wavelengths at the temperatures that the gas is at. And we use these trace molecules to see where the hydrogen gas is, to study its properties, and also to determine things like its motions and chemistry and so on. And the most commonly used molecule for these studies is carbon monoxide, because it is the most abundant molecule in space after hydrogen. So some of the data that I'll show you today will be from carbon monoxide. Now, carbon monoxide is actually a very handy molecule if you're a radio astronomer and you want to study a cold cloud, because it will produce emission lines as long as the gas is at least 5 degrees above absolute zero. And that's true for almost all of the gas, and so we're all set. And it produces a nice little picket fence of emission lines at different wavelengths, and the data I'll show you today will come from these two different particular transitions of carbon monoxide. So with that little overview of the physics processes, I want to give you a little taste of what the exciting science is that we can look at when we study the invisible universe. A key question in astronomy today concerns the origin of structure in the universe. And by origin of structure, I mean, how do things form? How do planets form? How do stars form? How does a galaxy form? Or even if we're very ambitious, we might ask, how does the universe itself form? Now, I'm not going to talk about the formation of the universe today. That's for Bob Abrams' talk in November. But I am going to focus primarily on star formation today, because to my mind, this is really central to those three formation questions. Because star formation is important for understanding both planet formation and galaxy formation. This is because what we know about planets suggests that they form in flattened disks of gas and dust around a young star as the young star is forming. And if you want to form a galaxy like our own Milky Way, well, what do you have to do? You have to form many billions of stars that will be the primary constituents of the galaxy. So star formation is really a central process in understanding how things form. Now, if we were to look at a cloud that's forming stars in our own galaxy, and we looked at it in visible light, we would see something rather like this black and white picture here shown on the left. In this picture, you see a field of bright stars in the disk of our Milky Way with a void in the middle. The void is not an absence of stars, it's actually the presence of a gas cloud. But the reason it appears as a void is because of those tiny dust grains that are mixed in with the gas. Those very fine dust grains are extremely good at absorbing and scattering light at visible wavelengths. So a star that's behind the cloud and the radiation is trying to get to us travels into the cloud, intersects a dust grain, meets a dust grain, and gets absorbed or scattered and never makes it through the cloud for our telescopes to pick it up. And so that's why we see the cloud in the visible light as an absence rather than a presence. If, however, we look at the same region of space at far infrared or radio wavelengths, the picture completely changes. The stars all disappear now, and what we see is the cloud of gas and dust itself glowing brightly by the emission from the dust grains, that continuum emission, and the spectral lines of the molecules in the dust. So these star-forming regions are dark in visible light, but glow brightly at far infrared and radio wavelengths. So with that general overview, I'd now like to talk about the first of my two science questions, which concerns star formation in our own backyard. And I'm going to start by talking a little bit about star formation in one of the nearest clouds of gas to the Sun, the cloud of gas in the constellation Orion. Now, Orion is a very familiar constellation to many amateur astronomers. It's probably the most well-known constellation in the Northern Hemisphere after the Big Dipper. It is a prominent winter constellation with these 8 bright stars arranged in a very distinctive pattern in the sky. If you look at the same region in Orion, not now in visible light, but at far infrared, this picture taken at 60 microns, it looks again completely different. And without the green asterisks to guide your eye and orient you between the two images, you would not know that you were looking at the same region of sky. The stars have disappeared, and what we see glowing brightly are the clouds of gas and dust in which we know many stars are forming. So this is a very large image. It's about 30 degrees across, so it's really a big swath of the sky. Orion's not up now, but if you were to go out and look at it in the winter, you would see just how big it is on the sky. To study star formation in Orion, what we need is a higher resolution image, more detail. And so we're going to zoom in to Orion, looking at this bright region in particular where lots of stars are forming, to try to look at some of the earliest stages in the process to form stars. To do that zoom in, we're going to use this telescope, the James Clerk Maxwell Telescope, which is located near the summit of Mauna Kea on the island of Hawaii. The JCMT is a 15-meter diameter radio telescope. It is the largest telescope on Mauna Kea. It works at wavelengths from 350 microns to 1.3 millimeters. And it is jointly operated by the UK, the Netherlands, and Canada. Canada's operations of the JCMT are managed by the Hertzberg Institute of Astrophysics, which is part of the National Research Council of Canada. For about 10 years, from 1996 until 2005, the JCMT was equipped with a very unique camera, which was known as SCUBA. And this camera was designed to take very sensitive and very accurate images of the sky at a wavelength of 850 microns. And it was very well suited to studying this heat emission from very cold dust grains in clouds of gas and dust in our own galaxy and in other galaxies. When SCUBA was on the JCMT, the combination of SCUBA plus the JCMT was by far the best submillimeter telescope in the world. SCUBA had to be decommissioned in 2005 due to irreparable problems with its cryogenic cooler system, but a new camera has been under construction for a while and is due on the telescope by the end of this year, SCUBA 2. And with SCUBA 2, we will again regain the pride of place of having the best telescope system in the world. SCUBA 2 has been jointly funded by the 3 countries, and in Canada, part of the funding for SCUBA 2 came from the Canadian Foundation for Innovation. So let me go back to Orion now. And this is this is a zoom in of Orion. This is an image of Orion at a wavelength of 850 microns. And notice the scale bar here. This arrow is about a half a degree. So we really have made a major zoom in compared to the wide field image I showed you a couple of slides ago. These 2 images are the same data, just shown with different stretches. The one on the left lets you see faint, fine structure, while the one that's on the right lets you see into the bright regions that are essentially overexposed in this rendition of the data. With SCUBA, when we look at the Orion cloud, we get an angular resolution of 15 arcseconds. And at the distance of Orion, which is about 1,500 light years away from the sun, this corresponds to a resolution on the sky of about 1/100th of a light year, or about 6,000 astronomical units. Now, an astronomical unit is the distance from the Earth to the sun. And the total size of our own solar system is about 100 to 200 astronomical units in diameter. So you can see that with SCUBA on the JCMT, we are not going to be able to identify and resolve individual solar systems in formation. We simply don't have enough angular resolution. But this resolution of 6,000 astronomical units is actually very well suited to studying the earliest phases of star formation, when you take a large cold cloud of gas and dust and it starts to collapse under its own gravity to become smaller and smaller and denser until eventually it forms a star. Now, one of the central problems in star formation today is understanding what sets the mass of the star as it forms. When we look at stars in our own galaxy, we observe that there's a very characteristic distribution of masses. Our sun is quite a normal star. There are lots of stars around like our sun. Stars that are 1/10 the mass of our sun are hugely common. They're everywhere. Stars that are 10 to 100 times more massive than our sun are very, very rare. And in fact, the exact distribution, how many stars of a certain mass do you find as a function of mass, is extremely uniform in all the regions in our galaxy that we found. And this uniformity is a puzzle. So if we wanted to understand how the mass of the star is set, one thing that makes sense is to look at the mass of the clumps of gas that we think are going to collapse to form a star. And so this was what Doug Johnstone and I and others did in looking at the gas in Orion. We looked at the masses of the clumps of gas in Orion. And this is a plot showing you how common the different types of stars are. So here's the mass of our sun, right about here. Out here at 10 times the mass of our sun, you can see only 1 to 2% by number. And up here at the top, the stars that are very low mass are very common. So this looks broadly similar to the distribution of the masses of the stars. In fact, is amazingly similar to the distribution of the masses of the stars, not just in the broad outline, but also in the details. And so this similarity between the masses of the gas clouds and the masses of young stars, which was seen not only in Orion, but in other nearby star-forming regions as well, led to a shift, a paradigm shift in star formation, where we thought we might understand now how the stellar masses are set, and the problem now is to determine how the masses of the gas clumps are set. That, in some ways, may be a more tractable problem because it involves taking a big blob of gas, watching it fragment, turbulence, magnetic fields. Actually, it doesn't sound very easy, but it is something that we can start to simulate on large computers, and a lot of that has been being done, some of that work here at McMaster. So this is a simple picture, and as I said, about 10 years ago, called a major paradigm shift in how we think about star formation. Now, some of these papers came out right around the time that Mike Reed was beginning his PhD, and Mike got interested in the question of how do massive stars form, the ones more massive than our sun. We can't study that in Orion because the massive gas clumps are too rare. And so what Mike and I did was to look at a couple of other clouds of gas, more distant, but more massive clouds that were able to form more massive stars. And one of the regions that Mike's looks at is shown here. This is the nebula M17. This again is a map made with scuba, now shown in a very pretty color scale as opposed to black and white. And in this image, we've identified again about 100 different clumps of gas, which are individually identified by the little colored symbols, which have to do with their temperature and whether or not there's evidence for a star present already. Now, when we look at M17, it's further away. And so we have poor spatial resolution. We are now at 30,000 AU resolution instead of 6,000 in Orion. And I'm going to come back to that in a minute. When we looked at the distribution of the masses of the clumps of gas, this picture ought to look somewhat familiar to you. It looks broadly like the plot for Orion. Low mass things more common, high mass things more rare, and a characteristic turnover at some mass. However, there's an important difference between M17 and Orion, and that's the position at which the turnover occurs. In M17, the turnover occurs at about a mass that's about 17 times the mass of our sun, whereas in Orion it was about the same as the mass of our sun. So if in M17 each clump formed one star, we wouldn't get the distribution of stellar masses that's observed. There would be too many high mass stars. The turnover point would be too high. So there's a couple of options for this, and this result is not unique to M17. It's seen in other regions that Mike analyzed for his thesis. One of the options is that our paradigm of one gas clump forms one star is too simple. And so that theory that was driven by the Orion and other observations might not be correct. The other option, though, comes back to the resolution that I mentioned. Because we have essentially a blurrier image in M17, if in Orion you had a few clouds of gas very close together, and then you observed them with a blurry image, you wouldn't be able to separate them out individually. You would see them as one larger structure. And so that could be a bias in our data for M17. There's nothing we can do about that. There is no telescope that we can currently use to make higher angular resolution images of M17. For that, we're going to need to wait for ALMA. So I'm now going to move on to the second science question, which concerns star formation in other galaxies. And I'm going to start by showing you some data for a few spiral galaxies that are broadly similar to our own Milky Way galaxy. These spiral galaxies here are all located in the Virgo cluster, which is the largest cluster of galaxies close to our sun. They are about 50 million light years away from us. These galaxies have been observed with the JCMT again, using a large survey that I'm leading that started a couple of years ago. So as a result, our spatial resolution is no longer measured in astronomical units. It's now measured in thousands of light years. So when we look at other galaxies, we cannot see a cloud of gas that's going to form one star. We can't even, with existing telescopes, separate out Orion, the entire region, from its neighbors. But what we can do is look in a broad overview at the entire disk of the galaxy and try to understand how star formation is regulated in the galactic disk. What is it that sets the rate at which stars form and drives the evolution of the galaxy into the future? So these four images, the orange background is an optical image where you can see in some cases very nice spiral arms and so on. And overlaid on them are contours. This is carbon monoxide emission showing you essentially where the molecular hydrogen is found. Looking at contour plots, I'm going to show you a few contour plots in the rest of my talk. Think of them as looking at a topographic map. In a topographic map where the peak of a mountain is, you get a collection of round contours. So where you see lots of contours together, like here in the center of M100, what that's showing you is a peak. It's a peak in the amount of gas. So there's more gas where there's more contours and less where there's less. Already we see some interesting differences from one galaxy to another in this sample of 4. This galaxy has lots of gas extended everywhere. In this one, it's concentrated in the spiral arms in the center. This galaxy is very centrally concentrated and actually has maybe been stripped of gas. This one we're not actually sure we've detected in the gas at all. So we can take those gas data and put them together with images of the star formation rate, which we have made using publicly available data, which were taken with both ground-based telescopes and the Spitzer Space Telescope. The data have been published and then kindly made available by the authors on a website, so anyone can download them and work with the images. So these images show you the star formation rate as a function of position in the 4 galaxies. Here again you see this galaxy very widespread. Here's the one with the spiral arms. Here's the truncated one. This one that we didn't detect is a little puzzling because there's a nice bright emission in the center. That's actually fooling us. It's not star formation. There's a massive black hole in the center of that galaxy, which is accreting gas from its surroundings, and that process can produce emission lines that mimic star formation. So when looking at this galaxy, you kind of have to ignore the blob in the center. So when we take the map of the star formation rate and we take the map of the amount of gas, one of the things that we can do is divide one by the other to get a map of how rapidly the gas is going to be used up in the galaxy. This essentially says if the gas that's in the galaxy today was not to be replenished by some other source, the outskirts of the galaxy, atomic hydrogen, other possible sources, how long before the galaxy runs out of gas? And that's what's shown in these color plots. This is showing you how long each galaxy has in each region before it runs out of gas. The interesting thing about this is not the absolute value, which is about 1 billion years, but the uniformity, both within a galaxy from place to place and from one galaxy to another. This uniformity, which has also been seen by another survey being carried out by a team from Europe, suggests to us that the star formation in galaxies is regulated very simply by the total amount of hydrogen gas that is available and in the correct state to form stars. Again, in some ways that sounds very simple and very obvious, but there have been a lot of very complicated theories advanced for the regulation of star formation in the disks of galaxies. And this very simple picture was not one of them, interestingly enough. So again, like in our studying star formation in our own solar neighborhood, we're led back to the question of, to understand star formation, we need to understand the gas. And in this case specifically, what regulates how much gas is in the proper phase to be available to form stars. Now, one of the really interesting things in looking at other galaxies is the ability to study extreme environments. And the most extreme environments occur when 2 galaxies collide. When 2 galaxies collide, we get an intense increase in the rate at which stars are being formed. It can be 100 or even 1,000 times higher than the rate that's being formed in our own galaxy. This huge increase in the star formation rate produces a large bump of radiation at the far infrared and submillimeter wavelengths and makes these objects very easy to study in the radio. But most of these colliding galaxies are also interesting because when we look at the early universe, we find many examples of dusty galaxies with huge rates of star formation. And we think these may be some of the earliest phases of galaxy formation, that they're forming their first generation of stars in a very intense burst. These galaxies at high redshift are so far away, they're back when the universe was about just a few billion years old. They're so far away that we cannot get very high spatial resolution on them. We can measure their global properties, but not much else. So to try to understand what it is that might trigger such a huge rate of star formation in these distant galaxies, we try to study the local analogs that are also in a burst phase to try to see if we can understand what drives the burst locally. Now, even the closest of the colliding galaxies are significantly farther away than the galaxies I showed you in the Virgo cluster. And so we no longer use telescopes like the JCMT, which is a single telescope. We now start to use arrays of radio telescopes like this one, the Caltech Millimeter Array, which is in Central California. By putting many telescopes together, we can achieve a much sharper image. The resolution of the image is no longer set by the size of the telescope, but by the separation between the telescopes, which is a very neat trick. So with this array, we can get 5 times better angular resolution than we could with the JCMT. So about 10 years ago, I was on sabbatical at Caltech, and I started a project there which was to study the gas properties of this colliding galaxy pair. This pair is known as the Antennae because of these long tidal tails. It's the closest example of a merger between 2 spiral galaxies. And in this zoomed up pretty picture from the Hubble Space Telescope, the nuclei of the 2 galaxies appear as the slightly redder regions, and kind of the remains of spiral arms and star formation show up as these bluer regions. The Antennae is also a very interesting system because it's forming very large numbers of young, massive star clusters. Clusters of stars 1 million to 10 million times the mass of our sun in a million stars that are only maybe 10 million years old. All galaxies contain massive star clusters, but most of those massive star clusters are about 10 billion years old. They were formed in the early universe. So by studying galaxies like the Antennae, we can also try to understand how those old clusters might have been formed. So to look at star formation in the Antennae and study the earliest phases, we looked again at where the molecular hydrogen was using carbon monoxide as a tracer. And this color contour map is just showing you the gas as an example. So here is the nucleus of one of the galaxies. Here's the nucleus of the other. It's rotated by about 90 degrees. I'm going to show you the two together in a minute. And a lot of gas is found in this region, which is not a region that stands out at all in the optical. And when we put the visible light image from the Hubble Space Telescope together with the radio image, you can, hopefully see on these screens the fine contour levels of the radio emission. This region with lots and lots of gas and dust is not very prominent at visible light, and that's just because there is so much gas and dust there. So I really like this picture, not just because I made it, but because it's a great example of the power of multi-wavelength astronomy. How by putting together data from visible light and radio, and sometimes X-ray and mid-infrared, you can learn a whole lot more about what's going on than you could by just working at one wavelength. So I'm kind of time's running along, so I'm not going to talk any more about that, except to say this is only one example of a colliding galaxy. We would like to study more. It's the closest, so we can't get really good resolution in the other galaxies, but we can put it in kind of a broad context by looking at a sample of nearby galaxies. And this was a project that I began on my second sabbatical, which was about 4 years ago now, when I spent the year in Hawaii working with the Submillimeter Array here, which is on the summit, near the summit of Mauna Kea. The JCMT is right about over here, just off the edge of the picture. The Submillimeter Array is a great telescope for studying these galaxy collisions because we can get higher angular resolution even than the previous array. and look at these galaxies that are out to 600 million light years with the same effective spatial resolution within the galaxy as we got with the JCMT and the Virgo cluster, about 3,000 light years. So a team I led of about 15 people carried out a survey of 14 of these colliding galaxy systems here. These are just little optical snapshots to give you an overview of your structure. You can see how messed up the galaxies are. Some of them really look like messy blobs. Very few of them look like regular spirals. These are all tidal perturbations from the interaction. These galaxies are all forming stars at a rate that is 60 to 600 times the rate in our own galaxy. And that's why we're interested in them. So this picture shows you 5 of the most luminous galaxies in our sample. The background black and white images are from the Hubble Space Telescope, and the red contours are showing you where the carbon monoxide is, and therefore by inference where the hydrogen gas is. In these galaxies that are fairly far along in their merger, all the gas has settled to the center. But in this galaxy where the merger is in an early phase and you can still see the 2 galaxies separately, there's gas found in the centers of the 2 galaxies. And this shows you an overview of 12 of the galaxies from our sample, showing you the range of morphologies. This is all just the gas emission, showing you where the hydrogen gas is. So we have very compact galaxies, we have galaxies that look more like the Antennae system with widely separated nuclei, and we have some that are kind of in between as well. So one of the things that we did was to look at these galaxies, look at the emission from carbon monoxide, compare it to a tracer of the star formation rate, and plot the amount of gas versus the star formation rate for the galaxies in our sample in comparison with the high redshift galaxies. The distant galaxies are up here, and some local spiral galaxies are down here. And these are just 2 plots showing you essentially the same data. The striking thing that we found was a nearly linear correlation between the 2 properties, between the amount of gas and the star formation rate, which again ties back to the Virgo observations, suggesting that how many stars are formed may be driven primarily by how much gas is in the correct state to go ahead and form stars. So we would like to be able to look at all these galaxies with the type of resolution we have in the Antennae to distinguish individual gas clouds, see if they contain very massive clouds like the Antennae, which was our theory for explaining the presence of very massive clusters. But we can't do that with existing telescopes. We've really, all the data I've shown you have been at the technological limit of the best telescopes in the world. So to go better, we need a better telescope. And that better telescope is the Atacama Large Millimeter Submillimeter Array. ALMA is a very special telescope. It's really the first example of an attempt to build a world observatory. ALMA is a collaboration between 3 major consortia between Europe, North America, and Asia. Canada is involved in ALMA with the North American partnership, which is Canada and the US. ALMA was the highest priority for a new ground-based facility in the Canadian Long-Range Plan for Astrophysics, which was a program that was led by Ralph Pudritz at the end of the 90s to lay out the priorities for Canadian facility development in astronomy for the next decade. I have been involved with ALMA since 1999 as the Canadian project scientist, and I can tell you that it is hugely exciting to see ALMA becoming real, to see real hardware and equipment and software and people arriving in Chile, and to see the rapid pace of development that's been taking place, particularly over the last couple of years. So ALMA is a multi-purpose observatory. It will be able to attempt to study any question in astronomy that requires the use of millimeter far infrared data. But ALMA was designed with 3 very top-level science goals in mind. And these science goals are what drives the technical specifications for ALMA. So I'm not going to go through these in detail, but just to summarize, the first goal is the ability to image the motions of the gas in a disk around a young star that could be forming planets. And this obviously would be extremely interesting because it would let us study the phases of planet formation directly, and would be a very complementary information to the data that we are getting on planets once they are formed from ground-based telescopes and from the Kepler Observatory that was mentioned in the introduction. The second high-level science goal is the ability to detect the emission from gas in a galaxy like our own Milky Way when it is at a redshift of 3, meaning looking back in time to when the universe was only a few billion years old. And this is obviously very exciting because it would let us study the evolution of a galaxy like our Milky Way from when it was just maybe a billion years old to the present, and would really open up and clarify our understanding of how galaxies form and evolve and get to be the way they are today. The third goal actually comes back to my point about multi-wavelength astronomy. We want to be able to make precise, accurate images at a resolution of 1/10 of an arcsecond. This resolution is chosen to match the resolution that is currently available from the Hubble Space Telescope and will be available through the James Webb Space Telescope, which is being launched, which should be launched sometime in the next decade, early in the next decade, and also matches the best resolution from ground-based telescopes equipped with adaptive optics. By having similar resolutions at many wavelengths, we open up new areas of science that we cannot really begin to study when we have a blurry image at one wavelength and a sharp one at another. So these science goals drive the technical specifications of ALMA. ALMA is going to be an array of 12-meter radio telescopes. There are going to be between 54 and 68 of them. The current contracts are for 54 antennas, but there is some thought that they may be able to find money to add on a few telescopes and build a few more, particularly in the US with some of the economic infrastructure funding that's available to the National Science Foundation. ALMA will be able to observe all the windows in the Earth's atmosphere from the ground from 10 millimeters up to 300 microns. And these are equipped with individual receivers. Canada is building the receivers that will work at a wavelength of 3 millimeters as our primary construction contribution to ALMA. We are building all the receivers for all of the antennas for ALMA. So that's about 75 receivers that they have to build for ALMA. Good angular resolution, good velocity resolution and bandwidth. The sensitivity won't mean much to you, but let me put it in context. Any object that the camera SCUBA on the JCMT can detect in about 8 hours of integration, ALMA can detect in 1 minute. So that basically means anything we already know about, we can study easily, higher resolution, be it a young star, being it a disk around a planet, being it a distant galaxy. ALMA has the sensitivity and the speed to do that. Construction is expected to be completed by the end of 2012 or early 2013, and the first science from ALMA will start to come out in 2011. One of the interesting things about building an array of telescopes is you don't have to wait for all the telescopes to be done. When you've got 10 or 15 of them, you're perfectly ready to start doing science. So we're going to start doing science with ALMA before all of the telescopes are built. So where is ALMA? ALMA is located in northern Chile. It is in the high desert near the historic town of San Pedro de Atacama. It's located at an elevation of about 5,000 meters. The reason for that is we need to get above as much of the Earth's atmosphere as we can because water vapor in the Earth's atmosphere is the killer for trying to observe at these radio wavelengths. I've been there. I can tell you it's hard to think at 5,000 meters and even harder to walk. ALMA is going to be a large array. We will be able to spread the telescopes out to be about 15 kilometers separate from each other. So you need quite a lot of real estate. And that's kind of indicated by this footprint. All the little dots here are showing you one early plan of where the antenna stations would be. This is a shot of the actual site for ALMA. It was taken in 1994. Very soon after the site was actually identified by astronomers, and they started to begin site testing to just see what a superb site it was. This is an artist's simulation of ALMA, showing you a portion of the main array with the large telescopes. Here's the little array of smaller telescopes, which was in the technical specifications that I didn't point out. Over here is a technical building at the high site. Because of the low oxygen content, the plan is to do as much as possible, not at the high site, but at an intermediate facility at about 3,000 meters. So only the most critical maintenance and only things that absolutely have to be at the high site, like the antenna and the spectrometer and so on, will actually be at the high site. And everyone working at the high site will be in oxygenated rooms, oxygenated trucks, or carrying oxygen packs, because you make mistakes so easily when you're oxygen deprived. This is a picture of the technical building at the high site. This will house the correlator, which is the machine for taking the data from the individual antennas, combining them, turning it into a spectrum, and sending it off to a computer to be saved. That correlator works at something over a gigabit per second, so it's an incredibly fast machine. And the data have to be stored and averaged in order to even think about having room to save them on a regular computer. This is a picture of one of the ALMA antennas. This is actually the first antenna built from the North American contract, the American contract. At the current time, there are 13 antennas, all at this intermediate site, in various stages of construction. 2 of the antennas have been completed, checked out by the vendors, and handed over to the project. The remaining ones are built and in the final testing stages, and in some cases kind of lying in pieces on the ground. But 13 antennas are there, and pretty soon there's going to be 1 antenna a month coming for a while. So the team is really going to have its hands full. I had a second nice picture which showed you 4 antennas, but it didn't show up on the Windows system, so I figured I'd better leave it. What do you do with a 12-meter antenna when you have to move it from one place to another? Well, you have to have an antenna transporter. And that's what this is. So picture this. This telescope is 12 meters across. I'm not sure how big 12 meters is. It's 12 of these seats or something. It's big. You drive in, you pick it up, and you carry it down the road. The front arms of this will hold 2 or 3 cars. I haven't seen one of these in person, but I've seen lots of pictures. It's very impressive. When I was out at the Submillimeter Array, I was up at the summit one time when they were moving their antennas, and their antennas are only 6 meters across. They have a similar machine to pick it up and move it to a new position and put it down. And it was very impressive. You're going down this road, and the road's tilting, and the hydraulics are keeping the antenna level, and it was just amazing. So this is really going to be a sight to see. The antennas are being constructed at 3,000 meters, tested there as far as they can be tested, and then these machines will drive them up the road to the high site. And once they're all on the high site, the machines will use them to move them from place to place on the summit as well. So I feel like I have to show you a picture of Canada's main contribution to ALMA construction, which is the receivers that work at 3 millimeters. This shows you one of the completed cartridges for the receivers. ALMA has a big cryostat. It's about 1 meter across that's kept very cold, only 3 degrees above absolute zero, because that's what we need for the receivers to work. And there are 10 different receivers ultimately that go in this cryostat, and it's big. So if one of the receivers develops a short and stops working, you don't want to have to warm up your entire cryostat, take it out and cool it down. That would take a couple of days. So the cryostat is designed so that each of the cartridges for a receiver kind of slides in a hole in the back. And when you need to replace one, you can pull it out the back, slide in a spare, and not interfere with the other receivers while they're still being kept cold. So this is showing you one of these cartridges. It would slide in and be at the back of the cryostat here. It's about 1 meter tall or so. That's how big this is. These graphs just show you some of the ALMA technical specifications. On this graph, you want to be below the line, and we are, which means we're more sensitive than the ALMA specification. Here, you want to be above the line, and we are, so that's good as well. The first 8 of these cartridges were built in-house at the Herzberg Institute of Astrophysics out in Victoria, British Columbia. And along the way, they developed the expertise and carried out technology transfer so that for the production run of 65 telescope receivers that will be necessary, including all the spares, many of the components of these receivers are being built in industry, and then they're being brought to HIA for the final assembly and the final testing before they go to the project. So there's been some really effective technology transfer going on there. And some of the companies have also gotten contracts for some of the components they've learned to build for other astronomy telescopes as well. So ALMA is going to be just a fantastic instrument for understanding the origin of structure in the universe. And this just gives you a list of some of the types of science questions that ALMA will be able to answer. We'll be able to look at planets forming in gas disks around stars. We'll be able to follow the process of exactly how gas funnels down into the center of one of these clouds to form a young star. We'll be able to look at large numbers of interacting galaxies with high angular resolution to understand exactly what is it in the merger process that triggers this intense burst of star formation. We will be able to look at galaxies like that one I showed you in Virgo with a massive black hole and see the gas that's funneling into the center of the black hole and understand a little bit more about the care and feeding of black holes in active galactic nuclei. And we will be able to study galaxy formation in the early universe and probably right the way forward to the present day. So ALMA is really going to revolutionize our knowledge of the invisible universe. And one of the things that I'm really looking forward to is in a few years being able to give public talks like this, including the first science results from ALMA. Thank you very much.